So welcome, college algebra students. This is my lesson for us on hyperbolas. And I know I've already asked you to look at the Khan Academy video, but I hope that this will help fill in some of the gaps and maybe be another way to talk about it. So as a second way to look at some of these. So first, why do we care about hyperbolas? That's a good question that we should address with each of these. And there are plenty of videos of this if you search YouTube. But when a plane will break the sound barrier, so if a jet will break the sound barrier, there ends up being this like compression of this, well, kind of wave going behind it. So it's like you'll be able to see it in the videos when you Google this or search this up on YouTube. There ends up being this like compression of the atmosphere around it, so it'll cause this condensation. So you can actually see basically then this cone that would start to form behind the jet. You're only going to see like a little piece of it here because then it's condensation again that you're not going to see it. But what's then going to happen is that compression that's going to be occurring, that you have this cone that's intersecting with a plane, which is the ground, which over short distances is relatively flat. We could be thinking of as a plane. So what that means is that the sonic boom is going to be traveling along the ground along a hyperbolic path. So it's not following the plane as like a line, so that if you were standing here or standing here, kind of on this perpendicular axis to that cone, that you would hear it at the same time. No, you'd actually hear it along the hyperbola, that slice, that kind of U shape at the same time. And so there's one example. There's some interesting connections here to aerospace design, things like that. Here's another really simple example. When you think about just the typical pencil with eraser, and you got the lead and you sharpen it, well, it's actually flat along these faces, right? Before you first sharpen it, it's got all these faces and they're flat. And then so what's going to happen is when you think about a pencil sharpener is actually a cone. And so you shove your pencil in, and it's going to grind this off until you get the sharpened point, which is what's happening at the end of your pencil. So what that means is that there's a curve along this flat edge where the cone starts to form from where the pencil sharpener kind of ground it down. So that shape right there must then be a hyperbola, because it's an intersection of a cone and a plane, the plane being the surface of that kind of flat piece going down the pencil. Another example, something that you can see, is if you would put a lamp really right next to the wall, and then so the way the light is emitting here from the center, kind of out in all directions, but it's going to be cut off by this shade of the lamp. But because of that, the way the light actually hits the wall is going to follow these hyperbolic paths. And what's different about this one is you actually get both branches of the hyperbola. So I think I used this language before, that there's a branch, two pieces. That's why this isn't a parabola. There's two pieces here to it. Okay. There's more. There's plenty more. I might add some in here for you, but so let's go in here and just as a moment of remembering that we're taking a cone and we're slicing it in different ways. And if we slice a cone such that the plane would be parallel to what the base would be, think about the circle base on the bottom. If I'm parallel to that, it's going to make a circle. Remember, it's not the inside, it's just where it's hitting the cone. If I tilt it a little bit and it cuts all the way through, so think about slicing it through at an angle that's not parallel to that base, then it makes an ellipse. And then if that slice ends up being parallel to the side, this line that's defining the cone, if I'm parallel to that, parabola, and anything that's really not ellipse or parabola is hyperbola, so it's just slightly tilting it in between those or beyond it. So if I tilt it a little bit beyond it, so if we think about a hyperbola, that plane of intersection of this cone is at a different angle than the parabola. And what's different, you might say, well, what's different about that again from the ellipse? Remember that the ellipse is only going to intersect half of it. Remember that this was really a thought of like two stacked cones. So like this. So the ellipse, it's going to slice through and it's never going to hit the other side. The hyperbola will, because remember these are defined by lines, so these are going out in all directions. So the hyperbola slices through the other side as well, which is why we get two pieces, two branches. And here, here are just images of what I just described. It doesn't have to be like slicing it vertical through the cone to generate a hyperbola. It's anything that's off of those parabola intersections, and it's not going to cut all the way through like an ellipse would. Okay, it's going to hit both sides. So a key thing here about hyperbolas. So here's a definition, and yes, as we do this, you should be taking notes. All of the assessments as of now, this could definitely change, but I'm planning them to be open notes, so you want to have good notes to refer back to this and not have to watch a video to come up with something. So hyperbolas are the set of all points whose difference from two fixed points is constant. Now that should sound a lot like the ellipse. The ellipse is the set of all points whose sum from two fixed points is constant. So that's really the fundamental difference. It's when we're looking at this this hyperbola shape. So I have a branch opening to the right. I have a branch opening to the left. It's almost like an ellipse that has been like flipped outward on itself is maybe a way to describe this. And you'll notice that there is no really this like minor axis that we'd have with ellipse with other points. I have no points here along this y-axis. Now another major difference is going to be that these two fixed points, which we're going to give the same name, foci, F-O-C-I, so with the ellipse, they were inside the shape. So with the hyperbola, they're still inside, but they're inside than the hyperbola, more like what you'd see for the parabola. Okay, so they're not in between the vertices, and so the vertices here are just what you'd think about for vertices of a parabola. They're that point where that U shape comes down and starts turning back the other direction. And so what's different then is that the distance, thinking about center to focus, do you notice that's more? So just as a quick reminder, when you think about an ellipse, so here's an ellipse that's longer in the x direction, that if I am moving from the center to the vertex, that's all the way out to the end point of the major axis. Remember that we called that A. And C is along the major axis, but it's less. That's the focus. So here, we're still going to call C the distance from the center to the focus. A is still the distance to the vertex, but in the hyperbola, C is bigger. So let's maybe put a little bit of that here. So C is the distance from the center to the focus. That's still true. A is the distance from the center to the vertex. That's still true. So there's not new labels for us to remember. Here's a picture of a hyperbola. This one's kind of rotated a little bit. So we have a center, and then we have something we're going to call a transverse axis. So the transverse axis is the line that is connecting, or let's say it this way, the line that goes through the foci. But that line also goes through the vertices. So the vertices and the foci are all on the transverse axis. Okay? There is this conjugate axis. And just like the ellipse, there is a point that is B, so that was the label we used before, away on the transverse axis. But that point actually is not on the hyperbola, but it does have an important feature to it. If we would connect a box between the vertices and these points B that are on this conjugate axis, this perpendicular axis. So if I make a box connecting them, now this is almost the work you would have done if you were making an ellipse, right? You would go left A, right A, up B, down B. And we would have tried to sketch in an ellipse in between those pieces. But here, for the hyperbola, what we're going to do is we're going to make this rectangle, and I'm going to construct in the diagonals of the rectangle. And as I do that, I drew that a little badly there. Let me fix that. As I do that, you'll notice that the diagonals of this box are asymptotes. Now, why would there be asymptotes for a hyperbola? If I go back up here and think about slicing a cone with a plane, do you notice that there definitely would be a connection between the lines that I would revolve to make the cone and then what the graph should be approaching? So basically, the asymptotes are representing here like the edges of the cone. And so as you're slicing through it with the hyperbola, you're getting closer and closer to the edge, but since the cone keeps getting bigger and keeps getting bigger, that's why you never really cut through the cone. Remember that it's on the inside. Okay, so more on that. But so I might write that B is the distance from center along the conjugate axis. And really that's just the other axis. That's the name given to it. But remember transverse, you can see it here. Transverse is the one with the foci and vertices. So B is the distance from the center along the other axis. Now when you think about the ellipse, we had a formula related in really A, B, and C. And that formula was based upon which one was the biggest. And remember in the ellipse, which one was the biggest? So think about that in the ellipse, A, B, or C. Remember A, center to vertex, C, center to focus, B, distance along the minor axis. So I hope you remember that that was A. So we wrote an equation for the ellipse. A squared is B squared plus C squared, and we kind of showed where that came from. Now, so that's the ellipse. For the hyperbola, though, when you think about what we just described, do you notice that C is bigger than A? In fact, in the hyperbola, c is the biggest. So the formula would be c squared equals a squared plus b squared. Okay, so there's the relationship between those measurements. Now here is a summary. This is what your book wrote, which is slightly different than what I just said, but still the same. So let's not worry too much about the words yet, but let's look right here. So I have an equation, x squared over a squared minus y squared over b squared equals 1. And that's an equation of a hyperbola. Notice that it's a lot like an ellipse. It looks like an ellipse, which looks like a circle. The primary difference is it's minus, not plus. Now, this will be a hyperbola that's opening left or right. And an easy way to remember that is that, do you notice that the x stuff here is the term that is positive, and the y stuff here is the term that's negative? So whichever one is the positive is the way it opens. So in this case, since the x stuff is positive, it's the opening kind of swallowing up the x-axis to the left and to the right. Now the book wrote b squared equals c squared minus a squared, but do you notice that's the same thing that I just wrote? Like if we would add a squared to both sides, so c squared is a squared plus b squared. So I'm just showing that. That's what the book is writing, but I'm more going to say c squared is a squared plus b squared. Okay. So vertices always correspond to the positive. B is a distance that you're moving along the conjugate axis, so if I would add to this picture, I could put a point here somewhere, and that would be B, and then a point along this y-axis down B, so that's minus B. And if I would draw a box between the vertices and those points between those two kind of U-shaped hyperbolas, and then construct the asymptotes by drawing the diagonals of the box, it's a way to kind of see the whole thing, the whole relationship. Okay. All right. Don't get too hung up on that yet. Let's look at an example, and we will go from there. So here's the first example. Find the equation of hyperbola with center at the origin, one focus at 4, 0, one vertex at -3, 0. Graph the equation. So I would always like to start these by drawing. So draw this with me. Pause the video if you need to write this down. But I like to just start plotting it. So I'm going to plot a point at 4, 0. So try to keep it to scale. So it says that that is a focus, so I'm just going to call that F1. And it says one vertex is at -3, 0, so I'll plot that. So -3, 0, and I'm going to call that V. I'm going to call that V2 actually. You can call it V1, doesn't matter. But there's the other vertex. Now, when you think about the hyperbola, there is symmetry on the top and the bottom, which means if there's a vertex at -3, 0, there must be one on the other side. Now here, I know that this is some hyperbola that's opening left or right. Sorry, that one's wrong. Left or right like this. And the reason, remember that the focus is always on the inside of the shape. So there's no other way to draw this so that the focus is on the inside. Like I can't draw hyperbola going up where that point -3, 0 is the vertex. Like it doesn't even really make sense. There's no way to really draw that. So this has to be a hyperbola opening left and right. And because of that, there's symmetry, which means if there's a vertex at -3, 0, there is one at 3, 0. And that's going to put then the focus on the inside. But if there's a focus at 4, 0, then there should be one on the other side as well, also inside. So that would be -4, 0. Okay. Now for this problem, there is some b value up here, which I don't know right now, which is defining these asymptotes for the hyperbola. Okay, so we're going to figure out what that is here in a second. So here's a rough sketch of it. Now, if I want to go ahead and come up with the equation, so the equation is either going to be x squared over a squared plus, minus y squared over b squared equals 1. Or, now if I wanted this, this is the, if you wrote this down, this should have been the equation you wrote when I said a horizontal transverse axis. And I'm going to abbreviate that HTA. If it's vertical, I should have clarified this at the moment, that I had said it's whichever one's positive, but what I didn't clarify is that A is always going to be with the piece that's positive. Okay, so this is not like the ellipse where you have to choose which one's bigger. It's actually going to always be the positive piece there. So I should have made that more clear. But so let's go ahead and continue here. So the center really is 0, 0. So if you wanted to, just like we did with the ellipse, you could say x minus 0 squared over, and here I need a squared. And I know it's a because it's the positive one. Okay, minus y minus 0 quantity squared over b squared, which I don't know, equals 1. Now, I hope, looking at this, you could decide what a is very, very quickly. If a is the distance from the center to the vertex, it doesn't matter which one I'm looking at, that the distance there is 3. So I now have x minus 0 squared over 9 minus y minus 0 quantity squared over, now I need b squared. Well, I just wrote this, that c squared, which must be the biggest, is the same thing as a squared plus b squared. Again, these are all built upon Pythagorean theorem, so it looks like that. You just have to remember which one's the biggest. And in the ellipse, a is bigger, so it's a squared equals, and in the hyperbola, c is the biggest, so it's c squared equals. And so for us, let's see, so a squared is 9, so, and c squared is 16. C is the distance from the center to the focus is at 4, 0, the center is at 0, 0. So I have 16 equals 9 plus b squared. Which means if I subtract 9 from both sides, that b squared is 7. Now you could solve that for b and say b is the square root of 7, but I need b squared for the equation, so save yourself a step and just put 7 there equals 1. Okay? So what that would say is if I was looking for this, these asymptotes, okay? So what that says is I should go up the y-axis from the center, square root of 7. So if I made a point at 0, comma square root of 7, and I go down from the center, negative square root of 7, and put a point there. And then I make a box between the vertices, which are at negative 3, 0, and 3, 0, and that square root of 7 and minus square root of 7, that the diagonals of that box will be the asymptotes that define the hyperbola. Now I'll say this, that the book, MyMathLab, for this text wants you to like find another point, like find a point over here. Like they might say, find when x is, I don't know, 5. And they would say, go to your equation and put a 5 in for x and solve. And if you put a 5 in for x and solve, it's going to give you two numbers. There's a plus or minus because there'll be a square root. And so what that will do is it'll tell you this y value and this y value that matches 5 comma whatever. The problem is none of those are really going to work out right. And even here, like the square root of 7, it's not a nice value. It's not clean. It's not easy. Um, it's not easy to plot is really what I'm trying to say. And the same thing's going to happen if you're trying to plot those points. So that is an alternative. So again, if I wanted to figure out exactly what this curve looked like, I could pick any number I want. I could pick 10, and I could go over to my equation that I wrote, and I could say, okay, x is 10. So I'd get 10 squared over 9 equals y squared over, minus y squared over 7 equals 1. So this is 100 over 9. I could move that to the other side. I could multiply by -7 on both sides, or divide if you think of it that way. Then take the square root, plus or minus. You'd have the +1 above and the -1 below the x-axis there. So that's an option that works. I like the asymptote method better because it's a consistent thing. So something else with the asymptotes, do you notice that you could come up with their equation? Don't think that that sounds complicated, because it really isn't. It's a line, first of all. So here for this one, I've drawn the line that has the positive slope from quadrant 3 to quadrant 1 between the corners of that box. So what is the slope of that line? Well, the slope of that line would be rise, which is going up along the conjugate axis, so that would be square root of 7. The run is how far over I have to go, and that should correspond to the vertex, because that should be the edge of the box. Well, in this case, that was 3. And this line has a y-intercept of 0. So the asymptote that I just described would be the square root of 7 over 3 times x plus 0. Then there's the other one, which is going to be almost just like it, except it's down and over, which means it should be negative square root of 7 over 3x plus 0. Okay. I'd encourage you also to take advantage of Desmos as you're doing this. Okay. So like right now, we could go to Desmos and we're going to type in x squared over 9 minus y squared over 7 equals 1. And then we're going to try to type in our two asymptotes, and we should see a very nice image, if all has gone well, of our hyperbolas with their asymptotes, and we could even show where the vertices here are. So again, x squared, I think that's 9. I'm forgetting the question. Y squared. Okay. So we have our hyperbola here, opening left to right from what Desmos is showing. And then if we go ahead and graph, so y equals, we have the square root of 7 over 3 x. And you can see there how nicely that is, make that dotted. You can see how nicely that is fitting, and you can see the asymptote behavior. And then if I graph the same thing here, and then say minus, and you get the other half. So again, these are connected to the cone. Like if you think about where we started these lessons the other day, if I said I took a line and I rotated it, spun it, or two lines and that are intersecting, and I start spinning them, we're generating that cone. So there's a connection definitely back to that I hope that you can appreciate here. Okay. So the last thing I just want to point out is, what if this hyperbola was opening up or down? Okay, and we would call that a vertical transverse axis. So now, just like with the ellipse, not much changes. So I'm not even going to do a full problem here. So the relationship is still the same. Again, the book put it backwards. I like to say c squared equals a squared plus b squared because it helps us keep track of the Pythagorean theorem. It is still a y squared and an x squared that are now subtracted, and you can see here from this little image that when the y's are the positive, right, this is the subtracted term, the x squared over b squared. So when the y's are positive, it's swallowing up the y-axis. In other words, there's a vertical transverse axis. Okay. A is still the distance from the center to the vertex. So I'm going to go up A and down A to get to that. Here I'm going to go left or right B along that conjugate axis to get those other points. And C is still the distance from the center to the focus. So again, the focus will be inside. Okay. So there's one last thing as we kind of finish this lesson here, which I hope is giving you a little bit of the connections that you're needing for the hyperbola. So let me get a Sketchpad file open. So here we have it, and so here is probably the most interesting thing about this constant difference. And this is an application that was actually created during World War II. And so I'm going to maybe hide a couple things here. I'm going to hide that. I'm going to hide those. Okay. So here's really the setup, and here's what they did during World War II. Think about that it's really important when there's an explosion somewhere to have an idea of where it came from. Now you might go, I know that was off in that direction, but how would you know how far it is? And so what I have here is a point that can move about, okay? And we're going to think about this as an explosion. This also works if we think about it being a lightning strike. Like when you think about lightning, you know, you see that almost instantaneously, you know, so if you're watching a storm. But the sound is only traveling about 1100 feet per second, which is very, very slow compared to light. And that means that, so once you see it, you can actually get a distance by just understanding that time. But it's a little bit different if you can't see it. So if there's just a mortar shell that explodes here in this point, how do I know it? How do I know where that is? And how do I know where that is quickly? So here's what they did in World War II, is that they would set up a little listening station here. Okay, so here's a listening station. All it was a microphone that would then record. It would record the sound, and they would record the time that it happened at. And then they did the same thing here. It's a microphone that's recording sound, and then they're recording the time that it happened at. So let's watch what happens here. So if I start the explosion, oh, I'm sorry, I lied. I want to move that out of the way. I thought that one was my explosion. I forgot I'd added another piece here. So here's my explosion. So I want this to occur somewhere random, okay? But assume I don't know where it is. So watch what happens. So the sound is actually radiating out in all directions. So because of that, as this circle expands and expands, it's going to get to one of the listening posts sooner than the other. Okay, so here it's already crossed over the green one as that sound wave is expanding out in all directions, but it hasn't yet reached the blue. So now they have both heard it because the wave has crossed the boundary of that circle, has crossed the blue listening post. So there's a time difference between the two, right? Blue heard it sooner than, green heard it sooner than blue. And so here's then what that means, and here's how this is a hyperbola, okay? So if I would draw a line from one listening post to the explosion and the other listening post to the explosion, okay? There is a distance that is different between those. For example, like if I start this explosion and I could stop it when I got exactly to the green one, there is some leftover distance here the explosion has to travel. And if I know sound travels at 1100 feet per second, and I would know the time difference, then I would know how far this is. So in my made-up example here, I'm saying that blue hears it 4 seconds later than green. So green has just heard it, the circle has expanded out and touched the green listening post, it's recorded, timestamped. There is 4 seconds to go until it reaches here. So think about what that means about the explosion. It must be 4,400 feet farther away from blue than green. If it's 4 seconds later and sound travels 1,100 feet per second, it is 4,400 feet between where the circle currently is to where it's still left to go. Okay. Now, that's assuming that you knew the explosion was in this spot. And the whole point of this was that you didn't know where the explosion was. So if I would hide this point and just say, okay, this explosion is somewhere, and right now this is a potential possibility for it. But all I need is that the difference of these segments to maintain this distance here that we're talking about. So if I need the difference to always be some idea of 4,400 because blue hears it 4 seconds later, then really what we're saying is that it is on some parabola. Hyperbola. Let me make that point bigger so you can see it. Like, so here's another possibility for that explosion. Like the explosion could have been right there on top of that point. And if I would start the explosion and I'd stop it right there, what that's saying is that this distance is still the same as what it was before. So I wouldn't know the explosion could be actually anywhere along this hyperbola. Now, I know it's not on the one over here, the other branch, and I hope you could say that too, that if I'm on the branch where this blue listening post is being swallowed up by it, then that means blue should have heard it first. But green heard it first, so it must be on the hyperbola closer to green. So I'm not going to make you do anything with this, but it's a really interesting connection as to how a hyperbola was practically used. Now you might, just for fun, think about, well, that doesn't seem super helpful because I don't know where on that hyperbola it is. Well, what they actually did, and that was my other random point here, is that they would then make a hyperbola using another point, and then it's got to be at the intersection of the hyperbola. So here I've created a new random point and made a hyperbola between green and red, and then that means the explosion must have been right there. So they would set up 3 of these listening posts to kind of triangulate, but in this case we're really using hyperbolas, so hyperbolas to generate the single point of where it must exist. Okay, so notice the constant difference, right? Because if one hears it sooner than the other, then there is a constant um, difference in the distance. Um, so an analogy might be this: if you're talking to somebody on the phone, not that you talk to many people on the phone probably, but if you would both hear a lightning strike in different positions, and one of you heard it on the phone before then you heard it in person, what you're talking about is that there's a constant difference, that the lightning must have struck 1,100 feet closer for every second for whoever heard it first. Do you know where it is? No, but it'll be somewhere on a hyperbola between the two people. So final comment is, notice that these fixed listening points are the foci of the hyperbola. So there's a little bit of fun with the hyperbola. Your expectation is that you're able to come up with the equations, decide if they're vertical or horizontal, find the missing components. I'm not going to do an example, but you should also be able to deal with the fact if the if the center moves from 0, 0. So dealing with an x minus h or a y minus k, and yes, they're still always x minus h and y minus k, which means the vertices, you're going to be adding a, again, to that center along that piece. So it's very consistent to the ellipse. So I hope that's helpful as you're looking at this, at least as another way to deal with this. So work on your My Math Lab. Talk to you later.